Alright, so let's continue this process of finding limits algebraically. We're going to use the technique of rationalizing the denominator or numerator of a fractional expression. Okay, so first of all, to do that, we're going to use something called the conjugate. You know, a conjugate is if I have something like, so let's say the conjugate of, say, the square root of a plus the square root of b is the square root of a minus the square root of b. That would be an example of a conjugate. And the thing about conjugates, if I multiply two conjugates together, that's going to, we say rationalize, get rid of the radicals. Okay, we say rationalize when we take the square root of a. If a is not a perfect square, then we have an irrational number, and that we have irrational value. But if I multiply these two expressions together, we're always going to get a rational expression. We can always get a rational expression. And you can see that if I multiply the square root of a plus the square root of b times the square root of a minus the square root of b, FOIL that out. What's the square root of a times the square root of a? First times first. Well, that's just going to be a. Square root of a times the square root of a is a. That's the definition of the square root of a. If I multiply the square root of a times itself, I get a. The outer is minus, right? Positive square root of a times negative square root of b is positive square root of a times the square root of b, or the square root of ab. The inner, though, is what? Positive b square root of b times square root of a. That's positive square root of a times square root of b. And what do you realize about these two things here? They combine to 0. Last is positive square root of b times negative square root of b, so that's minus b, right? Square root of b times square root of b is b. And so we're just left with a minus b, which is going to be rational, assuming a and b, of course, are rational numbers themselves. Okay, so this is the idea that we're going to make use of. So how exactly does this happen? Well, let's start with this example. First of all, what do we do first to find the limit as t approaches 0? We plug in 0, right, to see what we get. Up top I get 0, and down below this is 0, square root of 1 is 1, 1 minus 1, 0. This is 0 divided by 0 if I plug in. Right? And so how can I go anywhere with this? There's no factoring. What can I factor out here? But notice I've got the square root of 1 plus 3t, that's like my square root of a, minus, well, this is not the square root of something. Well, you can think of it, square root of 1 is 1. Right, so I'm not saying that both of a, square root of a and square root of b are both irrational. One of them may be rational. Okay. So what I'm going to do, though, is I'm going to multiply that that denominator in this case, right? I'm rationalizing the denominator by its conjugate. So what's the conjugate of the square root of 1 plus 3t minus 1? Well, it's the square root of 1 plus 3t. That doesn't change. But change this minus what? To a positive 1 plus 1. Okay. Now, whatever I do to the bottom, I can't just multiply the bottom by something. I have to multiply what? The top by it as well, because why? I can't change the expression. And when I do this, when I multiply by this, how much am I multiplying by? This whole thing right here is equal to 1, right? Looks crazy, but that's another way to write the number 1. And so, right, writing essentially fractions in different forms involves that process of multiplying by 1 to get an equivalent fraction, right? So that's sort of what we're doing here. Okay. Well, let's see what happens here. So here's my, don't forget my equal signs, right? This whole thing is equal to what? What do I do first? What should you write first? Limit. Don't forget the limit as t approaches 0. Now up top, I've got 2t, and I'm going to put in parentheses, right? Square root of 1 plus 3t plus 1. Okay, so this is multiplying. Now, you could distribute that through, right, the 2t over the addition here, but don't. Leave it factored. Remember, our goal is to find a common factor. In fact, when I plug in t equals 0, I got 0 over 0. I'm looking for a factor of t in the denominator. I've already got my t factor in the numerator, and I can cancel those out. That's my goal. So leave it factored. Leave it factored. Now down below I might have some work to do. Let's see what happens. Foil this out, right? So the square root of 1 plus 3t times the square root of 1 plus 3t is just what? 1 plus 3t. Right? It's just like the square root of a times the square root of a is a. So I get 1 plus 3t. And then what happens? The outer is positive, right? The square root of 1 plus 3t. And the inner is what? Negative the square root of 1 plus 3t. So those go to 0 just like we said here. Same thing. Last is negative 1 times positive 1. That's minus 1. Okay. Now, in the numerator, I can now simplify by combining like terms. And I will do that. One minus 1 is 0. I'm just left with 3t. With 3t. And now we see that common factor of t that was giving us trouble, right? When I still plug in 0 for t, I'm getting 0 over 0. But t divided by t is 1. Right? T divided by t is 1. And now the expression I have left over, which is just 2 times this stuff over 3, that is actually continuous at t equals 0. So I can now evaluate by doing direct substitution. When I do that, I don't write the limit sign anymore. So it's 2 times, in parentheses, 1 plus 3 times 0, just plugging in t is 0, plus 1, all over 3. Right. And so what is this? 1 plus 0 is 1, square root of 1 is 1, 1 plus 1 is 2, 2 times 2 is 4, divided by 3. 4/3 is our result. By the way, for improper fractions like 4/3, leave them like that. Don't write this as 1 and 1/3. Don't use mixed numbers. Don't approximate this as 1.3 or 1.33 or 1.333. Leave it as a improper fraction. Okay. Don't forget also you can confirm this limit. I mean, could you make a simple mistake somewhere in here? Sure, I make mistakes all the time too. But you can go back and numerically look at this limit, right, and do what we did when we were talking about limits numerically. Let t get close to 0 from above and below, and make sure it's approaching 4/3, which indeed is about 1.333, close to it. That's what you should be approaching. That is a good thing to get in the habit of doing. Let's look at another one. When I plug in x equal 2, 7 minus 2 is 5, square root of 5 minus square root of 5 is 0, 2 minus 2 is 0. There it is. As I said, we're looking at this 0 over 0 indeterminate form quite a bit here. Alright, so what do? I'm going to multiply by the conjugate. This time, since the radicals are in the numerator, I'm going to rationalize the numerator, and the conjugate I'm going to multiply by is the square root of 7 minus x, what? Change that minus what to a plus square root of 5. Notice the minus, the subtraction here changes sign, not in here. The 7 minus x doesn't become 7 plus x. Right, that's the a. The a, square root of a is 7 minus x minus square root of b is 5. Of course, whatever I do to the top, I have to do to the bottom as well. Again, that's equal to 1. Now, multiply by foiling across the top. Well, first of all, what should we do? Write our limit. Forget that. Multiplying the top, square root of 7 minus x times square root of 7 minus x is 7 minus x. The outer and inner terms are opposites, right? I get positive square root of 5 times the square root of 7 minus x, negative square root of 5 times the square root of 7 minus x. Those go to 0. Last times last, negative square root of 5 times positive square root of 5 is negative what? Square root of 5 times square root of 5 is 5. Down below, I've got x minus 2. I'm going to put that in parentheses now. That's important that I do that because I want to multiply it by. Now, it is tempting. We foiled across the top, right? We foiled across the top. It is tempting to foil down here. But remember, we don't want to foil down here. We want to leave this factored. Why? We need that x minus 2 factor because when I plugged in x equal 2, I got 0 in the denominator, and I want to keep that x minus 2 factor. So don't expand, leave it factor. Up top, simplify. What do I get? 7 minus 5 is 2. I get 2 minus x up top. Now, are these two factors, x minus 2 and 2 minus x, are they equal? Are they the same factor? Can I just cancel them out? The answer is no. So some of you know the answer, what has to happen here. When I cancel these out, I'm going to be left not with a factor of 1, but a factor of -1. And that's because x minus 2 and 2 minus x are just opposites. In other words, 2 minus x is equal to negative x minus 2. If you distribute this negative sign, you get negative x plus 2, and negative x plus 2 is the same as 2 minus x. So keep in mind that this thing here is the same thing as negative x minus 2. And so when I do the canceling here, the x minus 2 and the x minus 2 cancels, but I have this -1. And so this becomes the limit. I forgot my limit equal sign there. I said to use equal signs, and I didn't do it myself. So up top I've got not 1 but -1, and in the bottom 1 times this stuff, I just have this stuff. And now notice again I can plug in x equal 2. This is continuous. This function is exactly the same as the original function for all values of x except x equal 2, but this one is continuous at 2. If I plug in x equal 2, I get, this is of course the square root of 5. What is the square root of 5 plus the square root of 5? If you add, you get 2 square root of 5. Not multiplying, I'm adding. So there's our actual limit. And again, I want the exact value, which would be this. If you use your calculator to approximate what this is, that's fine, but you have to give this exact value. And the approximation can be used to check your self numerically, that's fine. Okay, there's our limit. Okay. So we've seen the technique of factoring or expanding and then factoring, the technique of rationalizing either the denominator or numerator as we did in these two examples. And now we'll look at simplifying a compound or complex fraction. So in this example, right, what do we call it, a compound or complex fraction? We've got a smaller fraction within the bigger fraction. And so our goal is really to get rid of that. Okay. Of course, plug in first though. With x is 0, I get 6 divided by 2 is 3, 3 minus 3 is 0, and so of course the denominator is 0. I'm in that indeterminate form. What I want to look at is, I'm going to simplify this and I'm going to show you two methods. Okay, here's method 1, which a lot of people have maybe seen. I don't know how many of you have dealt with compound or complex fractions, but here's one way we can do it. We can combine the numerator as one fraction. Let's just write this out here. Now I'm doing this without the limit sign. I'll come back to the limit sign in a minute here. But just want to focus on simplifying first. So what some people say is we can find a common denominator and subtract these two, and then I can just divide by x. Well, what is the common denominator? This is 3 really divided by 1 if you want to think of it that way. Well, the common denominator is just going to be x plus 2. So I need to multiply top and bottom of this fraction by x plus 2. Right, so this is still 3, but now I have this common denominator. I can subtract 6 minus 3 times the quantity x plus 2. And it'll be all over this common denominator. Still dividing that whole thing by x. And now what I want to do is clean this up. I want to distribute the -3 through here. And so what do I have up top here? I have 6 minus 3x minus 6, right? -3 times 2, don't forget to distribute that out. 6 minus 6 is 0, so what does the top simply become? The top simply becomes negative 3x over x plus 2. So I've accomplished the task of combining the numerator as one fraction. Right? So 6 divided by x plus 2 minus 3 is the same as negative 3x divided by x plus 2. Now, what do? How do I divide that by x? Well, remember, this is the same as x over 1 if you want to think about it that way. Dividing by a fraction is the same as what? Multiplying by what? The reciprocal. The reciprocal of x, or x over 1, is 1 over x. And now, notice I have a common factor in the numerator and denominator, right? Both of those will be canceled. X over x is equal to 1, and I'm just left with negative 3 over x plus 2. And this is true provided x is not equal to 0. We lost that information when we canceled that out, right? But here is the original expression. This is what it simplifies down to. So this function here is the same as this function for all values of x except 0. But we're going to be able to find the limit as x approaches 0 of this one by direct substitution, because this one is continuous at 0. Now, before we do that, though, I do want to show you method 2. And it's the method I typically use. Generally, it's a little bit simpler. And so here's what I'm going to do. I'm going to just rewrite the whole expression. And what I'm going to do this time is I'm going to clear out the compound fraction by multiplying the big fraction by 1 in the form of the least common denominator of all my little fractions over the least common denominator of my little fractions. So the only denominator, little fraction that matters is this x plus 2. This is 3 over 1, this is x over 1. So I've got 1, 1, and x plus 2. So I'm going to multiply the top and the bottom of this big fraction by x plus 2. Okay. Now, when I do that, the bottom just becomes x times x plus 2. And you could distribute x squared plus 2x, but I'm going to leave this factor down here. But here, notice there's a parentheses around this. I've got to distribute this x plus 2 over both of these things. Now, when x plus 2 gets multiplied by 6 over x plus 2, what happens? The x plus 2 in the denominator will cancel with this x plus 2, just leaving 6. When I multiply x plus 2 times the negative 3, I get negative 3 times x plus 2. And this numerator here looks kind of familiar. I hope you realize, right? If I distribute that negative 3, I get 6 minus 3x minus 6, which simplifies down to just negative 3x. Our denominator I've left factored, and the reason is because now notice this common x can come out, and lo and behold, we are at the same thing we were in method 1. Okay, I kind of like this method here. It's a little cleaner and smoother. Kind of see we got sort of an extra step in there with method 1. But if you feel more comfortable with method 1, that's fine. Either method will work. Okay. So now we're ready to give the answer to the original question, which was what's this limit as x approaches 0. So let's write that out. The limit as x approaches 0 of 6 divided by x plus 2 minus 3 all over x is equal to the limit as x approaches 0 of the function we've simplified down to, negative 3 over x plus 2. Right? But this one I can't evaluate the limit, because when I plug in, unlike this one where I get 0 over 0, this one I get what? Negative 3 over 0 plus 2, which is negative 3 halves. And there is the limit. And there's the limit. Okay, so those are the 3 techniques. In the next video, we're going to do some other things that can happen. Look at some combinations where we have to use more than one technique, and techniques where or limits where we have a parameter, another looks like a variable, but it's actual parameter. So we'll be talking about that in the next video.